Okay, so now we want to talk about the energy that can be stored in a spring. And so let's go back to our formula for the force on a spring. So that, let's say here's a wall, and then here is our spring, and then here is our mass M. Okay, and then our formula was that the force that was acting on a spring, okay, was equal to minus a spring constant, and then it was how far did you stretch the spring, so that it takes more and more and more force the further back that you try to pull this thing. So the spring has a natural length that it wants to have, and then when you pull it back a little bit, it's going to experience a force that's trying to pull the mass back to where it was to begin with. So that's what that negative sign means. And it would depend on the stiffness of the spring. So if this was a dinky rubber band, it wouldn't take very much force to be able to pull it out. But if this was a shock absorber that had a large spring constant, it would be very difficult to pull that spring out. So that's the force that it's going to take to pull it out. But what we're interested in is the energy that it would take to pull it out. So how much energy would you have to put into the spring in order to pull it? Now you might be tempted to think, well, if you pull it out, let's say you pull it out twice as far, according to this formula, it would take twice the amount of force. So 2 times the length would be 2 times the amount of force. So you might be tempted to think it's going to take 2 times the amount of energy, but it's not. So if you look at that formula there, E stands for energy, and it's going to depend on the spring constant, so we need to put the C in there, just like the formula for the spring force, and it is going to depend on how far you stretch it. So instead of delta L, we're going to use R. So R is going to be how far are you stretching it, but notice that it's not just R, it's R squared. Now, well, I'll explain why later. So in a future lesson, when we talk about the springs, we'll talk about that in a little bit more detail. But just take my word for it that it's going to be R squared. And then you also notice that it has a 1/2 in front of it. And so that actually comes out of the calculus of it. So if you go on, above algebra is trigonometry, and above trigonometry is calculus. And so if you take a calculus level physics class, you would learn why that 1/2 has to be in there. But it's important, it's part of the formula. So the amount of energy that it's going to take to pull back a spring is going to be depending on the size of the spring, that's the spring constant, how far back you pull it, and then remember that you have to square it. And so an example of this is going to be a bow. So that if you take a bow and you pull it back this far and you let it go, then the arrow is going to have a certain amount of energy. But if you pull it back 2 times further and you let it go, then that arrow is going to have how much energy? Sounds like a test question, doesn't it? So what would you do? You're pulling it back twice as far, so the R would be 2 times as much. But don't say that the energy is going to be 2 times as much, because what do you got to do to the R? You got to square it. So that means it's going to have 2 times 2 is 4. So it would have 4 times the amount of energy. And now let's say that you pull it back 3 times further. What's going to happen? Okay, so that it's going to be 3 times 3, which is 9. So it'll have 9 times as much energy. Notice that when we pull it back, we're changing the amplitude of it, so that this is the place where the spring wants to be. And so do you remember that we could draw a line through it like this, and that was the equilibrium? And then if we pull it back over to here, okay, we're increasing the amplitude. And then, so that was the reason why we said that the amplitude was proportional to the energy. I did not say that the amplitude was equal to the energy. I said it was proportional. So what does that mean? If you increase the amplitude, you increase the energy. So if I increase the R, I increase the amount of energy I give it to. Now I could give you this question on the exam. So I could say, take a rubber band and pull it back a certain distance and shoot a rock with it. Okay, then what would happen if I took 2 rubber bands and I wrap them around my finger and I pull it back the same distance? How much energy would it have? If I have 2 times the rubber bands, what would that do to C? It would make it twice as stiff. So this would go up by 2. So instead of C, it would be 2C. So what would the energy do? It would be 2. So notice that this does not have a squared term on it. So if this thing gets bigger, then this thing gets bigger. If this thing gets 2 times bigger, this thing gets 2 times bigger. But don't do it with the R, because the R is the one that has the squared term on it. All right, now you notice that this one has a yellow box around it, and so that means that on the exam I am not going to tell you pull it back this many meters and the spring constant is 3,000, calculate the energy in joules. You can, it's not that difficult, but I just think that as long as you understand it conceptually, you'll be okay. And so a bow is pulled back a certain distance with a certain amount of force. If it's pulled back half the distance, what amount of energy will it take? So notice that this time the R is not getting bigger, the R is getting smaller. So I need to take 1/2 and square it. So 1/2 squared is 1/4. So it's going to have 1/4 the original energy. So be able to do it either way. Either the R gets big or the R gets small. Okay, let's take a break, and when we come back, let's talk about damped harmonic motion.